on the assumption of elastic isotropic scattering in the center of mass system. Isotropic in the center of mass system. Estimate the Water-Kerma response function for a 1 MeV or for 0.1 MeV neutrons. How does this compare with the corresponding value for tissue given in Appendix D? Take scattering cross sections for hydrogen at this energy to be 12.8 barns, and oxygen 3.5 barns. So he has equation 5.13, I guess so do I. He reduces it differently. I'm going to do it my way. The Kerma response, this is equation 513, looks something like this. This is epsilon, I believe. Right? Yeah. Just so you guys can know what I'm.
Are those subscripts ij?
ij, yes, ij. So this summation is inside this summation.
Oh, I didn't see it. Okay, that makes sense. I didn't see the first summation.
So where I is for each element, and J for each interaction. We only have one type of interaction, so the J summation can go away. We don't care about that anymore. Also, there's no dependence on R, so not saying that it's a function of position. So to calculate this, what did I say, epsilon? I can never remember Greek letters. Epsilon. Using equation 515, 2EA over A plus 1 squared. Is that a real equation? Double check. This is for elastic.
Yes. Well, it's missing stuff. But
It's missing stuff.
times 1 minus F1 times at E.
You can get rid of that because it's isotropic.
Okay,
And
alright.
that's just the frequency of that, the way I understand it.
Yeah, if it's isotropic, I think you can drop that stuff.
Okay.
F1 of E is just 0 if it's isotropic, so you get 1.
Alright, alright, thanks. So for oxygen, so you're going to get 0.0111 MeV, and epsilon hydrogen 0.05 MeV. So I'm going to calculate in I over rho, no positional dependence, for each one, where N is the number of atoms per volume and P is mass per volume. So if N is atoms per volume and rho is mass per volume, we can say this value has units of atoms per mass. This makes something easier, I think. So this is equal to the mass fraction of the mixture. So the number of hydrogen over rho, well, mass fraction, let me say this real quick. The mass fraction, I'm just going to call that omega H is going to be 2 over 18, and omega for oxygen is going to be 16 over 18. That's just from the fact that oxygen molecules are, this is H2O, this is water. Okay, everyone okay with that? Okay. So, for hydrogen, we have 0.111, you can go as far as you want, grams of hydrogen per 1 gram of H2O times 1 gram of hydrogen per mole times Na. I've got this number. And you get, for hydrogen, 6.69 times 10 to the 22 atoms per gram. This is per gram of the water, per gram of water. In a similar way, you can calculate oxygen, and you get 3.35 times 10 to the 22 atoms per gram of water. This should make sense. In water, we have more hydrogen atoms than we do oxygen atoms. So for these two elements, our Kerma response, we're just going to expand out that formation, and we're going to get, this is still a function of energy, I think, yeah. It's going to be Na over NO over rho times sigma O times EO elastic plus NH over rho sigma H epsilon H elastic. Equals 7.07 times 10 to the negative 12 grays per centimeter squared. And the book value, you guys interpolate, it's going to be around 6.3, 7 or 6.4 times 10 to the negative 12 grays per centimeter cubed. So they're not too far off. So this is for water. The value in the book for tissue is slightly less. So it makes sense that tissue is, for Kerma, is somewhere around that of water, since we have a lot of water, a lot of hydrogen in us.
Which table was that in?
D8 I have on mine. D6, what it says in the solution. So one of those two tables. Either I'm wrong or
They're both D8.
okay. Excellent. But which one is Kerma again? What's the definition of Kerma?
Energy positive.
Energy positive. Okay. So the reason why epsilon is higher for hydrogen is because for a neutron, the hydrogen absorbs more energy from, or the hydrogen has the ability to absorb more energy from the neutron than the oxygen does.
Can you just walk through N naught over rho calculation again?
Yeah, I'll do that for oxygen.
I'm sorry.
No, that's fine. If something I do does not make sense, then let me know. What?
Nothing. Go on.
Okay. So for this, it's 0.8 8, 9.
And that's just the 16 over 18?
Yeah,
Okay.
8 over 9. Grams of oxygen per 1 gram of hydrogen, or water, sorry, times Na, which this is 6.022, times 10 to the 23 moles of hydrogen, and no, moles of oxygen, sorry. And there are 16 grams of oxygen per mole of oxygen, right? Moles cancel. Atoms per mole. Moles cancel, grams of oxygen cancel, and you get 3.35 times 10 to the 22 atoms of oxygen per gram of H2O. That makes sense? That answer your question? Okay. Anybody have any other questions on this? All right. If you guys